here. And are people online also? Is Jody online?
Jody won't.
Oh, perfect.
She's in.
Yes, sorry, and so maybe it was mentioned last week, but there's a conference coming up this weekend in Bellingham, Washington, related to SIAM, Pacific Northwest chapter, who's the vice president's right over there. And anyway, I think the students are practicing their talk. So anyway, I'll give the time over to Sandra, and then we'll hear from Patricia next. So thanks.
I'm delighted to stand before you today to present to you a project titled Choice of Model Error Variance for Data Assimilation in the Transport Equation. And my co-authors are Professor Babyale and Donna Kaufman, and a fellow student, Patricia Azike. In my presentation, I'll talk about the following. I'll talk about the four-dimensional variation data assimilation, the representer method with constraint data assimilation as regularization. Under that, I'll look at the different regularization parameters and methods. I'll look at the posterior objective functions. I'll show you some of the preliminary results. I'll conclude and then tell you some of my future work. And then I'll show you my references. Data assimilation is a critical issue in different scientific fields such as oceanography, meteorology, and atmospheric sciences. And its purpose is to combine observations with mathematical models in order to create accurate and consistent representations of physical processes. For this case, we use the weak constraint for dimension data assimilation in a preliminary study of Wildfire smoke transport. For this project, we use the transport equation as our model, and these models came 2.5 concentrations represented by small letter Q. And the model is shown above with initial and boundary conditions. And seen, U is the wind, represents the wind field, and our first Q represents wildfire smoke conditions. To do this data assimilation, we also assume that we have observations at endpoints in time and space, and that these observations can be expressed as the sum of true PM2.5 concentrations, small q, plus normally distributed errors, epsilon. When using the weak constraint data assimilation, we do assume that we have errors not only in the observations in the initial and boundary conditions, but also in our model due to unresolved processes in the forcing and parameterization. Therefore, our main aim is now to find a time evolving state of PM2.5 concentration that minimizes all those errors. And we can do that by minimizing the objective function, which is the weighted sum of squared error terms in the least squares sets. This cost function in terms of Q is equal to the sum of the error in the model, the squared error in the initial condition in the boundary, and then the observations, and substituting for those various errors to get the so-called expression, where the weights Wi, Wv, and W are then weights to the model, to the initial condition, boundary condition, and data respectively. To minimize this cost function, we do use calculus of variations, and in this we assume that Q hat is the optimal state that minimizes the objective function in terms of Q. And if Q hat is the minimizer of that objective function, it implies that the gradient of the cost function with respect to Q hat is equal to 0. Then doing that results into Euler-Lagrange systems of equations as shown above, where these deltas are Dirac delta functions, and Patricia will talk more about that. And as we can see, these two systems are coupled in that the variable lambda and q hat can also be found in this other system, and therefore we cannot solve them directly. We therefore we use the representer method to decouple the Euler-Lagrange systems of equations. In this method, we assume that the optimal state Q hat can be expressed as the sum of the first guess QF and the linear combination of representer functions Rm, where Bm are the unknown representer coefficients. QF is the solution to the error-free transport equation, and the representer functions can be obtained by solving this system forward in space and time. But as you can see, to solve this system, we need alpha L, which is the corresponding adjoint function. To obtain that, to obtain the adjoint functions, we solve the second system backward in time and space. So substituting this assumption into the Euler-Lagrange equations, the systems of equations, we do obtain the unknown representer coefficients beta L using this expression, and then substituting for the linear combination of representer functions, we do obtain the optimal state as this, which is the sum of the first guess, and we know how to obtain that, plus the multiplication of Patricia's H transpose, P inverse, and the representer vector R, and H is equal to the difference between the observations and the QF, and the first guess at the points where we obtain those observations. P is equal to the sum of the representer matrix plus the observation covariance, and this is a symmetric positive definite matrix. R is the vector of representer fields, and those are the various dimensions. To obtain the representer functions, we do need the model weight. The model weight initial and boundary condition weights, and also the beta weights. Therefore, the way in which we select those weights can significantly affect the optimal estimates, in that because these estimates do depend on the significantly change depending on the weight given to the model and to the data. As we can see in this example, we used periodic boundary conditions. We set the initial condition to be equal to 0, and use the constant wind field that is equal to 1, and add an exponential function as our foreseen with the different parameters as seen. And in this, we obtained a set of results. For this first case, we gave more weight to the data than to the model, and as a result, we see that the solution tends to fit the data. And for this case, we gave more weight to the model than to the data, and the solution fits the first case. Therefore, without using trial and error, how best can we choose the model error variance? This leads us to our new chapter, which is viewing constraint data assimilation as regularization. For this case, we assume that the initial and boundary conditions are exact, and that the optimal state is given by this expression, which is equal to the admin of the objective function in terms of Q, and this is equal to the summation of the squared error in the observation and then the error in the model. We name them differently as Z data, Q and J mod of Q. So to do the regularization, we do fit the data and then regularize using the transport equation with the regularization parameter equal to W over W, that is the weight in the model over the weight to the data. Therefore, the main aim is to find this parameter, and if we get this parameter, we can then get the model error variance. Some of the parameter selection methods we use are the L-curve, the discrepancy principle, and the chi-square method. For the L-curve, we do plot the regularization norm against the residual norm, that is J mod of Q hat now, against J data of Q hat. And the optimal parameter is one that corresponds to the value in the cone of the L shape. And for the discrepancy principle, the optimal parameter is that one that gives us J data of Q hat approximately equal to tau, which is a user input tolerance. And for the chi-square method, the optimal parameter, lambda optimal, is the one that gives us the objective function of Q hat that follows a chi-square method, a chi-square distribution of M, a chi-square distribution of M degrees of freedom, and this is approximately equal to M, where M is the number of observations. Okay. The beauty with using representer methods is that we don't need new expressions to find J hat data and J mod data, as those can be expressed in matrix forms, as we shall see. Considering the data penalty that is given as the sum of squared errors in the data, in matrix form, which is equals to Q hat minus D. Delta is the weight to the data, and then N is Q hat minus D. And from the definition of the representer coefficients, we obtain beta as given in terms of Q hat minus D. And therefore, substitute for Q hat minus D, it is equal to W inverse H, and this gives us this matrix notation for the J data of Q hat. For the model penalty, that is J mod in Q hat, we have the errors in the dynamics, in the initial condition and the boundary condition, and substituting for Q hat, we obtain this other expression that is in terms of QF and the representer and the weight of the representer functions. But remember, we said that QF is the solution with error-free representer to the error-free transport equation. Therefore, some of these terms go to 0. For example, this will go to 0. This will go to 0, and that will go to 0 to give us an expression only in terms of the vector of the presented points. Also from above, these equations were written in terms of from this we see that we can write this in terms of the adjoint. And therefore, substituting for the vector of representing the variance expression, our new expression is as seen, whereby these are matrices, and our main aim is to express this as a matrix where alpha is now the adjoint vector. We can do that using the idea of Green's functions, because the adjoint function alpha L is for point measurement, it's just a Green's function equal to small gamma with the various inputs, which satisfies this backward in time, backward in space system, and the corresponding representer functions satisfy the forward model. Therefore, we can then, therefore, we can then express this big gamma in terms of the representer, in terms of the Green's functions. And we can see that this big gamma is equal to this expression that is in terms of the representer function of the base functions, and this is equal to the representer functions at points Lm as functions of x and t. And therefore, this is equal to our expression that was in the J mod of Q hat, and therefore substituting for this with big R, we obtain the model penalty with respect to Q hat as H transpose P inverse R, P inverse H, and H and P still hold the previous definitions we defined earlier. These are we use the data penalty and the model penalty in the regularization selection techniques to obtain the optimal regularization parameter, that is to obtain the best choice of the model, of the weight to the model. So for these preliminary results, we obtained the parameter, we obtained the optimal parameter lambda using the chi-square method, and this gave us the model weight equal to 0.145, and then the weight to the data that was used is as shown above, and this gave us a chi-square value of 36.09, which is approximately equal to the number of observations because we used 36 observations. For these results, we used the same parameters as in we use these same parameters. We assumed periodic boundary conditions, zero initial condition, and constant wind field. And then the forcing was centered at x naught equal to 33. That's why, since our velocity was positive and x naught was centered at 33, the concentration at location 32 is quite low, since the concentration was now moving to the right. That's why for the various locations on the right of 33, we see that the concentrations are moving to the right as time goes on. And for this, the solution fits the data, because during regularization, we assumed that we are fitting the data and then regularizing using the transport equation. In this talk, I just wanted you to get a few points. Some of them being, it is important to get a good weight for the model when doing the constraint data assimilation, and we can use existing regularization parameter selection methods to calculate this weight, and the representer methods. And the representer method gives us a convenient way of finding that. And for the future work, I plan to apply this to 2D and then to smooth 3D. These are my references. Thank you.
Questions?
17 minutes. Oh.
Maybe 5 minutes per question or less, or more?
5. Then 5 for
Yeah.
questions.
I have a question on your slide, one of your early slides,
Okay.
and this is mostly just notation. Yeah, right here. So, under observations,
Yeah.
you call so DM is the observation.
Yeah.
And you call E the normally distributed error.
Yeah.
And I guess the way that that's written, and I actually talked about this with Patricia today too, it makes it look as if the model is correct and that the observation is somehow wrong.
Yeah, that is true.
But is that really right? I mean, it's our model that's wrong. This is more just terminology. It's not, you could leave the slide the way it is. I was curious how to think about that. Because the observation is what it is.
Yeah,
And it's true that there are errors. I mean, the observations have some stochastic, whatever, errors in them.
Mhm.
But when you write it like that, it makes it look like the observation is wrong.
so is it better to write it as the truth that this is what you think was the have?
No, I'm not sure. I'm not exactly sure what's the best way to write it. Anyway, this is more of a comment than anything.
I'll check it out.
Yeah.
Thank you.
Is it true that that you always have the same observation at the same place?
No, it is at different places, different times.
Okay, and that was accounted for?
Yeah.
Okay.
So in that testing question, is it a big data of new types? Is it like the total of the new types or just like?
Yeah, it is it is the product. The buildings. Is it like divergence?
There is a U times Q.
Yeah.
I thought it's like definitely U and S.
No, they're not together.
I'm curious where you got the data from.
It is estimated.
Okay.
Yeah. But we are planning to use data from the Environment Protection Agency. Yeah.
Yes, excuse me. In your one of the slides, you said you saw the IP problem. So yeah.
Mm.
So you solve it going forward to get your new set condition and solve the item back. Because you so identify what the type.
Yeah, we solved the representative functions forward in time, forward in space, and then this backward in time and backward in space. And these expressions come from substituting that into the Euler-Lagrange systems of equation.
So are those method conditions for this problem?
Yeah, this is you can say it is the final since it is at the last time.
And then you convert those times to zero.
Yeah, zero.
Is U provided?
The velocity,
Yeah. In all space and time?
Patricia is working.
Prescribed the necessity.
Yeah.
Okay.
Well, we're always going to use prescribed velocity fields. Just sometimes they're artificially prescribed.
All right, we should probably move on to the next, so thank you. Are you gonna use the same computer or different?
No, she will use the same label.
Jody's, no. Not there. Brian's logged in also.
Judge will just watch the video. Oh, are you going to just connect?
No, I don't have that thing. So
Send
I
it
just so it's in my email already. So I just
Do
have
you
to
need, thing?
It won't fit.
It won't fit.
What won't fit?
I don't have the.
No, I have this. And you plug that into this.
You can.
Oh,
If you want to use your computer, or do you want to use?
But you need to share the screen.
Oh, okay.
Are you on Zoom?
Brian sent me the.
Then
It doesn't matter. You can log into whatever you want.
You can join. Oh, sign in here.
Okay.
Joined?
Oh, it's not displaying on the screen.
If you join, then you'll need to share on this.
Because I want Zoom here.
Then open the Zoom and share the screen. Oh, you can't sign in here.
Just, yeah, you want to use this?
Yeah, because
Okay.
my Zoom is updating.
Gotcha.
Oh, this is you. Mhm.
Completed.
Yeah, from the same, click on that video, so, down then, the last one, yeah, click on that, and then log out.
Hello, everyone. My name is Patricia, and I'll be presenting on the topic modeling wildfire smoke transfer. So I have my advisor, Professor Donna, and Professor Jody, as well as Sandra. We're working together on this project. This is an overview of what I'll be talking about today. I'll be introducing wildfire smoke, as well as our transport model, Smoke 3D. I'll take us through some of the results we've gotten at the moment. I'll also be describing how we're incorporating data, using data assimilation, some challenges that we've faced so far, and the way forward. According to the NASA Earth Observatory on Fire, something on the Earth is always burning. And if we look at this map, we have the location of active fires around the world from 2000 to 2023 on a monthly basis. This was supposed to play. Sorry, I think it's not playing. So with this map, we can see that there's always fire at almost every time. This year alone, we've heard of fires in Morocco, in Mojave, and more recently in Maui. As this fire burns, smoke is released into the atmosphere, which contains harmful pollutants such as PM2.5. And the tiny size of PM2.5 allows it to flow into the lungs, causing respiratory diseases and sometimes death in sensitive groups. It's important for us to understand how smoke is being transported. This will help us to understand its past and present behavior, predict its impact with regards to the pollutant, and also make regulatory decisions in smoke management. And we simulate smoke transports using Smoke 3D. It's a three-dimensional model which we use to estimate concentrations of PM2.5. And the software platform of Smoke 3D implements the AMR features of Forest Claw, which is a multi-block hybrid parallel suite that refines on logically Cartesian meshes using patch-based solvers. With AMR, it allows for a dynamically adapted mesh that targets sensitive regions on the domain and refines to a higher precision where the solution is rapidly changing or coalescence. And one good thing about AMR is the structure creates a hierarchy of non-overlapping meshes, which are stored as leaves in connected tree-based mesh structures known as quad trees or up trees. And these tree structures facilitate efficient data structures that can handle complex geometries as well as parallelism, and then it makes it suitable for large-scale simulations. With Forest Claw, explicit time-stepping methods are implemented, as well as limiters, which help to suppress oscillations that arise in the solution. And because AMR targets the sensitive location on the domain where the solution exists, instead of searching around for it, the problem of over-resolving or under-resolving those regions is solved, and then ensuring accuracy while being computationally cost-effective.
So here we have an example of a patch in forest close. So it's non-overlapping. The patches are placed end to end, unlike what you have in a patchwork where they can be layered on top of each other. The refinement technique is really simple. First of all, the initial simulation is defined on a coarse grid, which is going to be advanced in time. And then the region to be refined or coarsened are tagged using certain metrics. You can have user-defined metrics, or you could just set up a threshold and then you check. In our case, we just refine wherever there's smoke. So wherever there's smoke, we refine, and where there's no smoke, we coarsen. And then because interactions take place between patches, which is facilitated by ghost cells, we first of all fill those ghost cells with data, and then the cell exchanges take place. When we want to move from a fine grid to a coarse grid, we simply average with the neighbor, we average to the value of the neighboring ghost cell. And when we want to move from a coarse grid to a finer grid, we use a constraint method of interpolation to artificially increase the resolution. And then at the end of the day, finer subgrids are put into those tagged regions. So very close to the solution. Very close to the solution, we have the finer grids, and then away from it, it's coarse. So the transport equation we implement in SMOK 3D is as shown. So Q is the concentration of PM2.5, which we're trying to estimate. We have our initial condition. We also use prescribed wind field data U, and S is the source term. It's basically any forcing that causes smoke to be injected into the atmosphere. We make use of the finite volume scheme. That's the numerical method of discretization. So we have QI is the cell average, and F is the flux, the average flux. So we use the wave propagation algorithm, which is implemented in CLOPAR, to obtain the approximation of this flux, which is really a Riemann problem. So we implement the transport equation in SMOK 3D, and we have our lat long grid. So we just selected the region of California. We used a Gaussian source term to indicate how smoke is being injected into the atmosphere when a fire starts, the prescribed velocity fields, and then we set a threshold to just refine wherever there's smoke. We also see a 3D simulation. We just conducted it over, we had an extruded mesh, and then we refined outwards. So in 2D, this is the AMR simulation in 2D. So at the beginning, at 0 seconds, there's no smoke, and then the force term has not started injecting smoke into the atmosphere, so we don't have any concentration. And then for whatever velocity that we use, whether we increase the speed or decrease it, the concentrations we got were almost the same. So in reality, the time is going to be with respect to whatever velocity we choose, and that's why I define it as T equal to T naught. Here, T equal to 2T naught and 3T naught. So it could be seconds, it could be hours, whatever velocities we choose at the end of the day. I'm sorry, this was supposed to play video, but the PDF formats, I don't know it's not Acrobat, so it's not playing. So this was just supposed to show how the simulation goes over time, and then it starts out small, increases and decreases based on whatever physics are governing it at that particular time. And then here's our extruded mesh in 3 dimensions. And so we have the concentration. And then the color bar the darker color simply represents where we have higher concentrations, and the lighter color is where we have lower concentrations at that particular point. Now, after doing all of this, because we want the results from our model to match real-life observations, we assimilate data, and this will help us to improve the accuracy of our model. We also assume that we have errors due to some unresolved processes. And then we indicate these errors by F and I. So the error in the model is represented by F, and the error in the initial condition is represented by I. And then, like Sandra stated earlier, we have observations, and then we assume that they do not perfectly match the results we get from our model. So we incorporate errors to denote that. At the end of the day, we are left with an optimization problem, and we want to obtain the best estimates that minimizes the differences that we get between our model and the observations. And this results in minimizing the cost function in least squared sense, as Sandra rightly described. And WF, WI, and WEQ are the weights. So these are associated with the errors that we have in the model and the initial condition. So we use the calculus of variations, and then we obtain the local extremum that corresponds to that best estimate. And this gives us a system of Euler-Lagrange equations. B represents the backward equation, and F is the forward equation. Lambda is simply the parameter we use to parameterize. Now, if we look closely at B and F, we see that we need Q. To solve for Q hat in F, we need the value of lambda. However, we still have Q here. So we can't exactly solve these equations directly. What we use is the method of representers. And this makes use of the linearity of those equations. So we can easily decouple it. And then the best estimate will simply be a linear combination of the exact solution of the transport equation and the representer functions. And these representer functions, they respond to the impulses that arise as a result of the differences between the model and the observations. And beta M is simply the coefficient of the representer functions. So when we rewrite it, we then have a new adjoint equation and forward equation. When we integrate the adjoint equation backward in time, we can then substitute and obtain the representer functions, which we can use to get our best estimate. However, we also need to know what delta X, the delta function here is. This is the source term for our adjoint equation. And because the delta function is itself a distribution, we need a function that we can use to adequately approximate that. So we need a function that can approximate this. And whatever function we are choosing, we have to make sure it satisfies the properties of the delta function, the normalization and the shifting property. So this is the normalization property, this is the shifting property. And the delta function really, it's infinite at 0 and then 0 every other place. So here we chose different, for the equation that we use to represent it, we use the heat kernel. And then epsilon is just helps us to define how sharp the Gaussian is. For whatever value of epsilon we pick, for really small epsilon, we want to make sure our delta function doesn't fall through, so we can be able to measure those impulses that occur as a result of the differences between the model, our model, and the observations. So if we look at this 1D description of the heat kernel, it's infinitely high. So at this point, it's really high. And then outside of 0, it's almost 0. So we tried to verify that in 2 dimensions. So we picked different values of n. We had n 16, 32, 64, and 128. And then we measured the error. So the difference between the heat kernel and 1. And then we observed that at this point, the delta function is smaller than the grid that we have chosen. So the error is really high at this point. But then towards this point, the middle here is really where we want to go because it's inside of our grid. At this edge, the delta function is bigger than the grid that we have. And so the errors climb back up. This is really, at this point, the grids are coarse. But with n equal to 64, for the values of epsilon between 10 raised to the power of -3 and 10 raised to the power of -2, we can have a good approximation to the delta function. And the order of accuracy is the order of h squared. And we use the midpoint rule for the integration using a cell-centered mesh. We also checked the shifting property, and regardless of the value of n, the order was of the order of epsilon. So the delta function we chose was effective. Now, going through smoke transport and the data assimilation, we've encountered some challenges. First of all is with the emission source. The characterization of the emissions is a source of uncertainty itself. Several researchers make assumptions in their model, and because we cannot describe all of the physics governing the equation, it leads to errors. Some researchers also rely on emission inventories. They just pick up constants, plug it in. So we don't have a sense of the equation they use to represent their emission source. And then smoke monitors are limited by their location. Another problem in the data assimilation is how we can store the adjoint solution. Because we need the adjoint solution in the forward solution, then we have to get a way to store the solution so that whenever we need it, we can easily pick it up. And then another problem is that the grids, the meshes for the adjoint and forward problems are different. And to be able to handle this, in the future, we want to incorporate some features in P4S, which handles the meshing. And then for the wind data, we want to use the mesh reader library to have good wind velocities. We'll be checkpointing the adjoint solution so we can easily store the solution of the adjoints to implement in the forward problem. And we want to define the delta function on a sphere. So we're trying to get a good approximation of the equation on the sphere. These are some of my references. Thank you.
Exactly, is it that you're minimizing the Wildfire cost equations?
So we are minimizing the cost function, the difference between the delta, the data, and our model. So we want to get the smallest error between the data observations and our model. Which of the equation? Okay.
I wonder if it is possible to use different equations approach to tackle the problem, and also to Sandra. I don't know if there is a way to refer to unit symmetry analysis to study such systems.
Yeah.
So the equations are solved, we discretize the individual equations. But you might be talking about something else where you actually, and I don't know too much about this, but you actually formulate a discrete system and then take, say, the transpose of that system as somehow related to an adjoint. I mean, there are ways to do that as well, but that's not, I don't think that really applies here. We have a time-dependent problem.
Yeah,
I think, but I'm not totally sure what you mean.
yeah, for some of the Lagrangian system, it's possible to use a symmetry method, find the symmetries and needed by the system, and then from the symmetry one can get the solution.
Okay. I guess I'm not really sure.
Yeah.
Maybe Sandra will try it.
And also the same technique is a user with a different equations.
Equations.
Yeah.
Right. think Sandra is the one that will really check that out.
The advantage of this approach, though, is that we don't have to do that, because we end up, in the end, you end up solving a really small system of equations for these betas, so it might be on the order of the number of observations you have. So we're not trying to invert large systems that depend on the entire state of the whole system.
What's an extruded mesh?
So from our 2D model, we simply extruded outwards the surface we just set an elevation to extrude out. So it gives us the illusion of a 3-dimensional system. Yes, but we're trying to work on the 3D system itself.
You almost have the full 3D
And
object.
does the 3D stuff is gonna account for topography?
We just try to we're trying to imagine just maybe 10 meters above the surface.
So with the extruded mesh, we can handle the project.
Okay,
We haven't yet here, but
so the extruded mesh is not 3 dimensions.
no, it is.
It is.
So it's just a stacked mesh on top of each other? I don't know what it is. Extruded mesh is. Still, sorry.
Because the way I understand it is if we have a 2D system and then we can extrude out and then it becomes 3D using the elevation we use.
That column that you're extruding up will have the
yes.
same value all the way.
All the way, yes.
So I guess maybe it's more relevant for AMR, because we're doing adaptive meshing in 2 dimensions. And then
Yeah.
And then I don't know what the sifting property of the Gaussian is. What's that?
Oh, okay. So this is the sifting property that when you multiply f of psi times the delta function of psi, which is shifted or sifted, it approximates f of x.
Okay, I mean, I know that, but I didn't know it's called sifting. So, okay, sorry. And then I guess the question is on this like experiment you did, like, I mean, I'm assuming you're gonna want to use AMR mesh, but everything you presented was for a fixed mesh or for an AMR mesh?
So this one
No,
here
no,
now.
the picture with it, like, showing how good the properties are with
Uh,
this one.
Oh, that was on a fixed mesh. Yeah, but we want to be able to do it. We're trying to see how we can do it in Smoke 3D because we have to refine with respect to epsilon as well. And so far, with the values of epsilon, we have to be careful in choosing epsilon because it could just fall through. So that's like one of the challenges we're having.
Okay. But you don't actually have to compute this delta function, this integral of this, do you? Do you actually do this convolution, which is actually
To show that.
is a convolution, the delta function, but sifting, you have to do this
Yes.
in the code?
No, we just showed this
Okay.
I just showed this in MATLAB. Any other questions?
Speaker, yeah? And thanks everyone for coming.
Yeah.
I'm gonna skip that too.